we probably ought to figure out how to interact with it, right? So what I want to talk about this morning is interactive AI. So how we support the communication between humans and AI. So you've probably heard of the black box problem, right? And Adam gave us a nice preview of that. These algorithms, they're like black boxes in the sense that it's pretty hard to understand what's going on inside of there, right? So we have the human working with the machine learning algorithm, and the black box problem describes this idea that the opaqueness of these algorithms, right? And so we read in the reading group, we read the paper by one of our keynote speakers, Jenna Burrell, and she talks about this notion of opaqueness and all the issues of not being able to see inside the algorithm and understand what it's doing, right? And Adam gave us a really nice overview of the whole sort of explainable AI agenda and how we can peek inside these algorithms and see what's going on in there using visualization and so on. And so thanks, Adam, for giving us a really good idea of that problem of explainable AI and some of the solutions that are available to us for that. But I guess the point the main claim I sort of want to make this morning is that, well, that's really only half the problem, right? And in fact, what I want to claim is that in fact we have a two black box problem in interactive AI. That not only is the machine learning like a black box, that it's hard for the human to see what's going on inside the algorithm, but isn't the human mind also a kind of black box? And isn't it equally as hard for the machine learning to understand what's going on in the analyst's mind? What is the analyst's reasoning process? What are they thinking about? What are their motivations? What are their goals? What are they trying to accomplish in this analysis? And so what I want to talk about is having humans and machines working together to do data analytics problems, right? To deal with big quantities of data. And so the real question is what is this interface between these two black boxes, okay? So we have the explainable AI arrow going this way, but we have a different arrow going this way. I'll call it explainable CI, explainable cognitive intelligence, right? As opposed to artificial intelligence. Our colleagues at the NSA call it explainable IA, explainable intelligence analysis. We've been running a workshop for the last, for 2 years now at the Viz conference called Machine Learning from User Interaction and Visualization. So another thing you might call that is MLUI, but that's sort of a terrible acronym. So I kind of like explainable CI a little bit better. So that's the sort of problem I want to present here, and I think this is a really hard problem, right? Because we're dealing with these two black boxes and how they talk together, right? So if we really want to achieve interactive AI, we got to solve this problem of these two blue arrows here, kind of simultaneously. And so one method for solving this problem, or at least partially solving it, is an approach that we like to call semantic interaction. And so that's kind of what I want to talk through today, is how semantic interaction addresses this two black box problem. And in particular, I want to talk about some of the challenges associated with this two black box problem and their associated design guidelines of how we can address those challenges. And I'm going to talk about 5 of those challenges. I'm going to talk about an overall challenge of just how we structure this space. I'm going to talk about a challenge that has to do with, well, how do we get the thinking out of the analyst's head and towards the algorithm? How do we put that into the algorithm? How do we extract out what the algorithm is doing? And how do we put that into the analyst's head, right? So those are kind of the 5 areas of challenges that I want to talk about today and how we're addressing those with semantic interaction. All right, so that's kind of the big picture of where we're going today. So the scenario that we're going to look at as I go through these 5 challenges is one of being, so picture yourself as an intelligence analyst working in the federal government. You're presented with a whole bunch of snippets, intelligence reports gathered from the field, and your goal is to figure out what are the bad guys planning, right? How do we figure out what they're planning and stop them, right? The tool that we've developed, Spire or Cosmos, kind of 2 different takes on this problem, looks kind of like this, and it is designed to support this challenge of an intelligence analyst trying to figure out what the bad guys are doing based on a whole bunch of textual information. So you got this big pile of textual documents. You're trying to sort through it and figure out what's going on in there and make a hypothesis from that information. So it's a text analysis problem, and you're trying to make sense out of this. And the tool we're going to talk about as we go through this, the sort of running example as I talk through these challenges, is going to be the Spire tool, which presents documents like this in a big space, open documents that the analyst has read, and close small icons here of documents that the system is kind of recommending or pointing the user to, and some connections and all this kind of stuff. So kind of a visual space for doing this kind of work. Okay, so that's the scenario that I want you to have in your head as we go through this. And so the first challenge that I want to talk about is sort of the overall challenge of just how we structure this communication between human black box and algorithm black box. And so kind of two ways of thinking about that. A way that you may have heard this phrase, human in the loop, is one way to think about that problem. I think the connotation of thinking about it that way is that the machine is sort of the center of the problem solving, and the human is there as kind of a consultant, right? Human in the loop. The algorithm's figuring this thing out, and every once in a while it has to consult a human to get some feedback so it can really figure out the answer, right? And so that's kind of, the foreground, background approach to structuring this space. As an HCI researcher, I just can't buy that approach, right? So I tend to like to think about it the other way around. And maybe the way to think about this is machine in the loop. The user is kind of the foreground. We want to design a human-centered space. And then the question is how do we sort of fit the algorithms in to that human's problem-solving process, right? So take a more human-centered approach to the problem of this communication between these two black boxes, okay? And so one implication of that sort of human-centered approach is to think about, well, what is it that the human is doing as they're trying to do this intelligence analysis problem, right? And so one such thing that we could look at is Paroli and Card's sense-making loop. So this is a model of the cognitive process that an intelligence analyst goes through as they're working through a problem like the one I described. And it's called the sense-making loop. And it kind of maps out the steps that an analyst goes through, everything from bringing in external data sources, going through kind of whittling it down to relevant information, extracting out relevant information, forming schemas out of that, turning that into some kind of hypothesis about what's going on, and eventually giving a presentation or writing a report for his or her boss, right? And just some things to notice about this is over here, there's kind of what we like to call the foraging loop, right? So this is primarily about finding relevant information, right? This is primarily what I like to call the synthesis loop, which is primarily about putting information together to build hypotheses, to create structure, right? And these two loops interact here in this kind of tricky process called dual search, which is this idea that you're simultaneously trying to create hypotheses out of the given data and at the same time trying to find data that supports the given hypotheses, right? You're trying to do those two things at the same time, which is a pretty cognitively gnarly problem if you think about it. So I think when we come at this sort of human in the loop, machine in the loop structuring of the problem, what we want to do is think about this sense-making loop as the focus, right? As the center of the problem. And our goal then is to take this process, which the human is trying to do, and then just plug algorithms in here to help this process along, right? And so we like to call this kind of facetiously, instead of human in the loop, we call it human is the loop, right? To sort of emphasize the fact that the human is sort of the center of the design, and it's all about how the algorithms fit into that loop, right? And so in particular, one way we're dealing with that problem in tools like Spire is that we're modeling this foraging cognitive loop as a form of relevance model, and we're modeling this synthesis cognitive loop as a form of dimension reduction and or clustering and or graph simplification and a variety of other models that we've tried to plug in here to model this this cognitive loop in a computational way, right? So we're plugging these computational algorithms into this human loop. Okay, is this making sense? So that's a human center. So I think the design guideline here for this, just how we structure this space of this communication between the two black boxes, is really one about structuring it with the human workflow as the center of the problem, and then how we plug the algorithms into that. Okay? So that's sort of guideline number one. Human is the loop, right? Challenge number two was, well, how do we see inside the black box of the human mind, right? How do we see what the analyst is doing, or what they're thinking, rather? And so here we appeal to some very useful cognitive principles, namely distributed cognition, embodied cognition. The idea that as people think, people externalize their thought processes into the physical space around them, right? And so what you're seeing here is an analyst working on a large display system doing this exact problem, right? He's got all these little intelligent snippets here. These are all little documents. And the analyst is starting to organize those documents by structuring them in this big two-dimensional space, right? So he's creating clusters, creating different kinds of spaces here, right? Arranging them across the space in a big two-dimensional. You could think of that as some kind of dimension reduction process, right? And so the analyst is doing this in a manual way, using the space to help them structure the data, right? And so this is helping them think through what's going on in these documents. They're probably putting a pile over here. Well, these documents are all about this guy who seems to be doing something suspicious, right? These documents are about this other guy who's doing something else suspicious over here. And these documents are kind of in between because they may relate these two guys doing suspicious things and maybe how they might be working together, right? And so they're creating structure out of this chaos, right? In this workspace. So I think what's neat about this? So if we observe analysts, we'll see them doing this process of organizing the space like this. And so I think what's neat about this is this gives us a kind of window into their cognition. We're actually seeing this person think, right? I'm going to show a little video here to just kind of see if we can actually see it, right? So this is a high-speed playback of a particular analyst going through one of these problem scenarios. Purely manual. We're just playing with documents and organizing them in the space, and you can kind of watch the analyst build structure out of chaos. And what that's giving us is this window into their thought process, right? We're starting to see what structures they're creating, right? What they're thinking about. We can even see the process of how they're thinking about that, how they're slowly building up their understanding of this space. That play for a little bit. So a couple of cool things about this. So we call this phenomenon space to think, where you can actually observe people doing this kind of thing, and you can actually get a window into their cognition. And a couple of neat things about this, I think, is that, well, okay, so humans think in space. Well, algorithms compute on space. Guess what? We can use space as a kind of common ground, right, between these two, a communication space, right? So suddenly we now have common ground to enable these two black boxes to start to understand each other, right? One way we've done that is we've modeled this as a dimension reduction process. So we can actually learn how the analyst is organizing this space, and then use that in a dimension reduction algorithm to help the analyst by projecting additional information into their space so that it actually fits right into their mental model of things. I'll come to that in a bit, a little bit of a preview. So we call this space to think, right? So this is sort of guideline number 2 of how to address this problem of extracting the thought process out of the human black box, okay? And And of course, we can do this. You don't have to have a big screen like Christopher has here. We've explored this in 3D environments with Doug Bowman. We've explored this in smaller, regular laptop spaces with Leanna House. Now we're exploring this in the context of writing a report with Carlos Avia. So there's lots of ways we see people creating these spaces to think. It doesn't have to be Chris's fancy screen there. So that brings me then to sort of problem challenge number 3 is, well, how do we get this input into the algorithm, right? So we can kind of see it happening. We can see it, we can extract it from the user by seeing them use these 2D spaces to externalize their cognition. So the next problem is, well, how do we get that into the algorithm? And so what I want to talk about here is that a big challenge when we're interacting with algorithms is, I like to talk about it in terms of the low-level nature of the parameters of the algorithms. And Adam hinted at this, right? That, like, for example, a really simple example, when you want to use a k-means algorithm, well, you got to choose k, right? It's a pretty low-level parameter. You got to pick that in order to use the algorithm. In the case of these kinds of dimension reduction spaces on textual data, modeling them as bags of words, oftentimes the features that we're interacting with are words. These are low-level features. Are we really going to ask a user to start their analysis by choosing some words to upweight and asking them to figure out what words they want to weight in this algorithm to get the projection that they want of their data? I don't think, see, that's a very low level of thinking, and that's at the level that the algorithms are thinking at. And so there's this kind of mismatch between the high-level thinking that the analyst is doing and this sort of low-level modeling that the algorithms are doing, right? And so that's kind of a challenge. How do we overcome this sort of high-level thought process to low-level thought process mismatch, right? And so specifically what we're not doing, I'll start with the wrong thing, is asking the user to go directly interact with these models. So let me just talk through this. So we've got data coming through. We're doing some relevance computation on that to find data relevant to what the user is doing in the space. We then project it right into the user space using a dimension reduction display layout model of some sort. We display that in some sort of spatialization, and then the user sees that and interacts with it. What we don't want to do is give the user some knobs on these algorithms, some low-level knobs, like what's the weight on this word, right, in this dimension reduction algorithm. That would be a lot of knobs, right, Adam? That would be thousands of knobs, all of which don't really mean anything to the user, right? So do we really want to present the user with 1,000 knobs on weights on words? Probably not, right? So that's what we're saying not to do. So what we want to do instead is exploit all these kinds of interactions that the user is doing anyway when they're analyzing this kind of information. So interactions like, hey, I'm creating clusters. I'm putting these documents together. I think these things are related. So I'm actually moving them near each other, right? Or, hey, I think this is important. I'm highlighting this with my yellow highlighter. Or, hey, I had an idea about this document. I'm going to type in some notes. I'm going to annotate this document in the margin, right? Or, hey, I really want to search on some stuff and find some relevant information. Type in some keywords, right? And do a Google search or whatever, right? These are all things that the analyst is doing anyway as they're analyzing they're performing this sense-making task. So why don't we use those interactions as the ones to manipulate the model, right? And so in particular, what we're doing is taking those spatial reorganization interactions of, these seem related, these seem related, this seems to kind of go between those. It's kind of related to both. Well, we can invert our dimension reduction to actually learn a projection. How is the user organizing things? What are we can actually learn what the weights on the keywords would have to be in order to produce that projection that the user is creating, right? And so we can use machine learning techniques then to learn this model based on these interactions that the user is doing anyway. Other kinds of interactions might be a little bit different, like, hey, I'm searching on some stuff, or I'm annotating, or I'm highlighting some stuff. Well, maybe that's maybe a weak form of machine learning where I can recast those kinds of interactions into underlying parameter knob turning things without the user having to turn those knobs themselves, right? And so we can take these high-level interactions that the analyst is doing and then do some learning or other kinds of manipulation on those in order to recast them into operations on the underlying algorithms, okay? So that's our kind of our guideline. Number 3 for how to deal with this high-level, low-level mismatch of input, you know, from the arrow from the human to the algorithm, is this notion of contextualized input, right? So as the user is doing their space to think, and as they're interacting in that space of organizing the information, we're using those interactions to drive the algorithms, not some knob turning on low-level parameters that they don't understand. Okay? Contextualized input. Fourth challenge is, okay, so now we've gone and we've computed. We've taken these inputs and we've computed some update on the models. And now what do we do with that? Well, guess what? Now we can use our forward models to project that information right into the space, right? So a simple little example is, so the user says, oh, wait, I think these things are related. I'm going to kind of build a cluster here. I'm going to put these things together, right? So the user creates this little cluster, and the system does 2 things under the hood. First of all, it learns based on this change to the dimension reduction that the user has made, what the user might really be interested in those documents. For example, things that might be common between those documents, shared words, for example. Then it uses that to do 2 things. One, it uses it to query out to a much bigger database of potentially relevant documents, bring the most relevant ones in, project them onto the screen, and project them onto the right spot on the screen, right? So some new documents related to that cluster might fill right into that cluster saying, hey, if you think this is important and you think you're building a cluster here of a topic you think is important, well, here's some other things you might want to read that are very related to that, right? Or this other document that was maybe a little further away, maybe not quite related, gets sucked in and said, well, this one's very relevant too. You should take another look at that, right? These others maybe kind of push away saying, oh, those are about something else. Maybe we'll put those over there somewhere. They're less relevant to what you're talking about here, right? So now what we've done is we've enabled the algorithms to think in the same space that the user is thinking in, right? So the user's space to think now becomes also the algorithm's space to think. And the mental model of the user is merged with the mental model of the algorithm, all in this common space. So we've contextualized the output of the machine learning right into the thought space of the analyst. Okay? So I'm going to call that principle number 4, is contextualize the output into the user's mental model. Okay? In contrast to, say, showing some information in some other screen, I get some other visualization that has relevant stuff in it, or something like that. Okay? So that helps me then sort of interpret what the output of the visualizations is. I can interpret that. Hey, it's right there. It's related to those guys. I better read that, right? Yeah. Okay. Another kind of angle of this is that, okay, so the machine learning is learning some stuff under the hood about what's important to me as an analyst as I'm doing this. And sure, it's projecting some useful stuff in here and kind of like a recommender system. And sure, it's integrated right into my thought space so I can see how it's all related to what I'm thinking about. But how do I get kind of an idea of what the algorithm's thinking, right? How do I get an idea of what it thinks is important? Is it agreeing with me? Well, so one way we've thought about that. So as the analyst is doing this work, the models are learning a set of weights on underlying terms, right? It's a bag of words representation. Each of these words or phrases has a weight associated with it, and that's what's determining this high-dimensional distance function, which is then causing things to be placed near or far from each other in this thought space. Well, so how does the user get an idea of what the algorithm thinks is important? What does it think I think is important, right? Well, guess what? down here in the documents, we can directly view that as some sort of automatic highlighting on the words themselves in the documents. Right? So we can see that, the algorithm has learned that this word endangered is really important to me. Is it really? Okay, yeah, I agree with that. That makes sense. Okay? And some of these other words get highlighted. Oh, here's some of the key players I was thinking about. And sure enough, it's picked up on their names, right? And it's highlighting those for me. So not only does it sort of help me just scan through these documents and find the important stuff, but it also helps me kind of confirm that it's agreeing with me, right? Or that we're honing in on the same ideas. I think something else that's neat about this is it helps me start to formalize my ideas, right? I was thinking, yeah, there's something going on here, right? These documents, I'm putting these together because there's some suspicious activities here, and these seem to be about the same kind of, maybe this activity is supporting this other suspicious activity, right? Well, hey, now this is helping me actually see some specific people and some specific activities that they might be doing, right? So it's helping me formalize it down to the sort of specific name level, not just some high-level thoughts I might have about some suspicious activity, right? So it's helping me drill down in that sense. Okay, so that's another example, I think, of contextualized output. Not only am I contextualizing maybe documents into my think space, right? But it's also contextualizing these model weights into the document space here, right? So that brings me to point number 5. So I think challenge number 5 really is then, well, how does this affect the analyst's thinking, right? How does this then plug back into my thinking as an analyst and help me? And the guideline here has to do with this notion of incremental formalism. Right? So when an analyst starts out the process, they don't know what this data is about. They just have some rough ideas. Maybe they have some task they're working on of trying to find some suspicious activity related to a certain person or something like that. So they usually have some starting information, but they really don't know what's going on. Right? So they start with this sort of really rough picture of what's going on, and they start to organize things, and they start to make sense out of it. And over time, they start building clusters, and they start better understanding the space. By the time they get to the end, they've got it all figured out, and they understand they've got this whole hypothesis, and they can stand here and tell you a story about what they've discovered, and what the bad guys are doing, and what we should do to stop them, and all that kind of stuff. And they kind of have the story represented in this visual way. Right? And so the analysts went through this process that we like to call incremental formalism, of gradually sort of figuring out what's going on. Right? And they're gradually formalizing their thoughts in the sense of the space. They're gradually formalizing their thoughts in the sense of what words are important, right? Who the key players are, all those kinds of things. So by the time they get to the end, they've got some real specifics, right? Some real crunchy stuff. They can say, this person's working with that person in order to do this activity. Right? Now, what's neat about this is that as the user is going through this incremental formalization process of learning about the data and figuring it out, well, guess what? The algorithm's doing the same thing. The algorithms under the hood are also going through this incremental learning process of gradually figuring out what's important to the analyst, what's not important to the analyst, right? So we could actually even see a time series plot of, for example, what words are becoming more important to the analyst and what words are becoming less important, and so on. And we can even match those two up, right? We can actually match up the analyst's learning process as they go through their process with this algorithm's learning process as it goes through its learning process as well. And so what that means is we've got to design our algorithms in such a way to support this incremental process, right? A lot of algorithms are designed, hey, if it's going to learn something, you get a batch learn, right? Here's a whole pile of data, learn, right? Give me the answer, right? Batch mode. We got to redesign the algorithms to think about how to learn incrementally from little bits of interaction along the way, right? Little small pieces of feedback over an extended period of time, where it's learning along with me, and as I'm doing these little bits of interactions and I'm learning little bits of things, it's learning little bits of things and giving me little bits of feedback along the way, right? Supporting that interactive loop. Okay, does that make sense? Okay, so there's 5 kinds of challenges and 5 kinds of guidelines I think we can apply in order to how to better design interactive AI. And I just want to talk a little bit about some of the sort of kind of cool outcomes we see as a result of this. So one kind of neat thing is has to do with trust, right? So how to say this? So if I were to just take this answer and just tell it to an analyst right up front, guess what? They wouldn't believe it. They wouldn't say, they wouldn't agree that that's the answer, right? But if the analyst goes through this process and gets to this point, they'll believe that that's the answer. Why? Because they went through the incremental formalism process, because they went through the hard work of going through this process to getting to here. And so they understood what it, right, all the steps it took to get here. And so by the time they get here, they agree that yeah, that's the solution, right? And so this collaborative process of incremental formalism, I think, is what builds trust of the user with the algorithm, right? And so I think maybe that's a better way to think about it than sort of the human in the loop style, where hey, we just present some results and maybe we try to explain it really well. But I think if the user's more in the loop, and if the user is the loop, then they'll trust the results, right? And they'll agree with the algorithm, right? And the algorithm will agree with them, right? So I think there's something to be said here about, I think there's a lot of work that could be done here in sort of measuring that. And, can we actually, for example, compare, maybe one analyst's work to another, or could we use that maybe for an expert analyst to train some newbie analyst who's just joined the organization or things like that. I kind of feel like this trust that's built up through incremental formalism may obviate some of the need for a lot of the explainable AI stuff. So maybe that's just something to think about. But maybe this solves the explainable AI problem in a different way. Okay. Something else that I think is neat that we've observed in running studies with this and watching analysts use these kind of systems is this high-level, low-level, the development of high-level, low-level roles, right? And so, for example, when we talk to the analyst after they've completed their analysis, and we ask them, well, what did you discover, right? They'll describe their hypothesis in very, very sort of high-level language, right? They'll say, well, I think these guys are going to attack such and such, right? And it's going to be terrible, right? We think these are the methods they're going to use and all that kind of stuff. And so they'll describe it from a conceptual level, right? But if we look at then what the algorithm has learned at the end of the session, right? The algorithm will point to a bunch of terms that are important. And so while the analyst has described it at this high conceptual level, the algorithm is describing it at this very low detail level. These are all the words that are important. This person, that thing, this type of weapon, right? All that kind of stuff. And so I think this develops a nice synergy, right? In fact, what we observed is kind of, we had a hard way to describe it. We had trouble figuring out how to describe this, but we described it as semantic synonyms. Right? That these were high-level concepts that were kind of semantic synonyms of these low-level concepts, so they were related, but just at different levels of abstraction. Right? And so I think this is a neat way to think about interactive AI as this notion of allowing the analyst freeing the analyst from all the low-level nitty-gritty work, allowing them to focus their attention on the high-level concepts, and letting the algorithm fill in all the details. Oh, here's the evidence for that, and things like that, okay? So I think this is a nice way to think about interactive AI as a notion of high-level and low-level roles between these two. Yeah. I guess one other thought is that I think that's something neat about these techniques is that because the algorithm is learning alongside the user, we can then actually use that to quantify some notion of bias, right, of what the user has learned, right? And so, for example, we can actually show the weights on the keywords that the user is, that has resulted at the end of the user's process. And then we could think about, well, Right? Are those the right weights, right? Or we can compare two different analysts and see, well, hey, you came up with this totally different model than I did, right? We can actually quantitatively compare those two and measure differences and so on. And might be able to relate that to things about the analyst and so on. And I think Leanna's done some nice work on, hey, we can actually, measure things about, how certain is the analyst or is the model that these things are related to each other and so on, and how we can present that back to the user. So I think all these neat outcomes then come out of this ability to enable this interactive AI between the models and the humans. Okay. So I think with that, I'll just say, yeah, thanks to all the awesome students who actually figured it out. And we'll have a few minutes for questions. How are we doing on time? Oh, okay. I went a little long. Sorry. Scott.
So we might be a year too late for this. I had a truth side workshop a year ago, and the trust and truth notion that you put up there seemed to go hand in hand. I worry about this path and the human sort of picking and choosing things would enable you to sort of filter out things that disagree with what you wish to believe.
Right.
What is it in here that allows that, encourages that not to happen?
Yeah, I think that's a good point, right? So if the user's driving the learning, right, what things did the user miss, right? And are we just learning, one particular take on things, right? So yeah, it's a great question. I think there's a lot of possibilities there, right? So first of all, let's back up. Is it really just confirming what the user is proposing? And I'd say actually, maybe not. So for example, if I put some things together and I say, well, I think something's going on here. So the relevance models will find stuff that would support that, but it might also find stuff that disagrees with that, right? It might find other evidence, right? If I say Scott is a great mountain climber, right? Maybe I'll find things about Scott being a mountain climber, but maybe I'll also find things about Scott doing other kinds of activities that might suggest, well, maybe he's not so into mountain climbing, right? Or hiking, I guess, is your thing, right? So I think the relevance models can handle that kind of not just confirming evidence, but disconfirming evidence. And I think that's also an area of research, certainly in the information retrieval community, right, to create algorithms that will find both confirming and disconfirming evidence and project those into the thought space, right? So I think there's a lot of room there for possibilities for research to handle those kind of problems. But I think, sort of orthogonal to that is just the idea of the quantification of bias bullet, is that we can actually measure those kind of things. Like we could detect that you never looked at blah, right? That was never upweighted in your process. You never even considered it. You might want to consider it, right? And so because we have the whole process quantified, I think we can do process level analysis to show trends like that in the process and suggest alternatives and all those kinds of things. I think there's a lot of room there for cool new work.
Okay. Thank you very much, Chris. And we will have time for more questions and answers when we get to the breakout groups. That's the whole purpose of having that. So if you like Chris's work and you want to talk to him, be sure to chase him. And our next faculty presentation is from Ewing. Ewing is a professor of history and Associate Dean for Graduate Studies and Research at the College of Liberal Arts and Human Sciences. I heard that's a pretty fancy college, but what do I know about that?
Thank you for the plug. So thank you very much to Tonu and to Carlos for the opportunity to come and talk to this group. This presentation is available as a Google Slides presentation. If you go to the website ethomasewing.org and then Data and Social Context, you can find it there. I appreciate the chance to follow the two presentations by Adam and Chris, because I think that what I'm trying to do is very much in dialogue with other scholars and across fields, and also with students. So I do appreciate the chance to hear those. Unfortunately, I teach a class at 12:30, so I'm going to have to leave, and then I'm going to Washington tonight on the bus, so I'm not going to be able to come to very much more of the symposium, which I appreciate is bad form. But I really wanted the chance to be able to talk with this group because I see the relationship between humans and computers as obviously one of the most important challenges of the 21st century, and both as researchers and educators, we absolutely have to deal with that and to think about that, and it's exactly this kind of workshop that's really pushing us to delve into these issues and come up with explanations. And as a historian, I very much appreciate the chance to work across disciplines and to be in this dialogue across these different fields. As a historian, I, of course, like books, and so I did bring some books with me that I'll be talking about briefly. Unfortunately, I have to go back to the library when I'm done, but you're welcome to go into the library, those of you who are here at Virginia Tech, and look at them and check them out anytime you want. But that's why I had to borrow a table up here, because these may be the largest books, at least the first one that we own. Okay, so I'm going to be talking about the 1890 census. In this census, the United States Census, and this census is, I think, widely recognized. It's significant in a couple of ways. The first is by genealogists, and they hate this census. I'm looking at Professor Kurt Luther here because I'm sure he's dealt with this. The reason they hate it is because all of the individual records were destroyed in a fire in 1921. They were stored in the basement of a building in Washington, D.C. It caught on fire. There's a nice illustration here on the right, the damage on the left, and they're gone. There were a few remaining. There were some that were damaged, and they actually destroyed all of those later on. And so out of the 65 million or so citizens of the United States, there are only about 6,000 records from the census that are available, and you can see an example here. So for genealogists trying to trace their family back, there's a big gap between the 1880 census and the 1900 census, and they just can't get to the 1890 census. But what did come out of the 1890 census and has been preserved are the statistical records, right? So not the individual records, but the data that came out of that census that was collected and tabulated and analyzed and then printed in bound volumes, some of which we still have in the library, others available online. I'll talk more about that in just a minute. And this is how I got interested in this census, because I was doing a project on the Russian influenza, which starts in Russia in late 1889 and hits the United States in early 1890, so January, February, March, which is right in the middle of the census year. So the census year starts in June of 1889 and ends in May of 1890. And so if you're interested in why people died in early 1890, that puts you right in the middle of the census data. And so I was using that information to do some research on mortality statistics, and this is an article that's going to come out in Influenza and Other Respiratory Viruses at some point. And so that was how I got interested in the census. When I saw the call for proposals for this workshop, there was another question I was interested in, which is the 1890 census is the first time that machines were used to do the counting. And so the title of this talk, Electricity Will Do the Counting, comes from one of the articles about this census. Okay, it's the first time that data was not counted only by hand by humans. They actually introduced a machine into this process. So if we go back to Chris's machine in the loop, now there is a machine in the loop. Previously, there never had been. So that was what I initially thought I was going to present on today, and it still is. But there's a second part to this, which is the question of race. And as historians and sociologists and theorists keep coming back to this question about the relationship between crime and punishment and criminology and race in contemporary America, they go back into history and they keep asking these questions about how does the process of counting criminality and attributing criminality along racial lines, how does that contribute to the development of what's been called a scientific racism? Okay, the way that racism is justified by scientific data, scientific methods, and so on. And the 1890 census is a key moment in this process. Okay, not only because of the data that was collected in the census, but also because what that provoked over the next 20, 30 years in terms of how statisticians looked at race and crime, but also how prominent African American social theorists challenged those views. And W.B. Du Bois has an amazing collection of data visualizations that directly challenges this presumed relationship between race and crime in this era. And so what I'm going to talk about today is this relationship between machine tabulation and also statistics and race. And I'll have to admit, and Carlos and Tanu know this, almost all of these two parts of the research have been done since I saw the call for proposals in late February, early March, I don't know. I'm still trying to figure it out right up through last night and this morning, and we'll continue to do so. Okay, so the 6 questions that were posed in submitting a paper for this conference, I rewrote a little bit because I wanted them to be able to take history into account. Okay, so not just how do we do this in the future, but how has the relationship between humans and algorithms mattered in the past? And how can learning from that experience and those processes shape the way we think about algorithms in the present and into the future? So these are basically the questions, just slightly reworded. And the argument I make is that you have to think about context. And I appreciate Chris finishing with talking about contextualization as a process, because that's exactly what we're interested in. This actually began for me as an undergraduate teaching. We have a course called Introduction to Data in Social Context, and so it really caused me to think a lot about that. Some of the books, Carlos, that you put up at the beginning have been central to the development of that course. This quotation from Kathy O'Neill, Weapons of Mass Destruction, was on a poster that we did a couple weeks ago, last week, for another conference. I love the fact that she takes what used to be the Virginia Tech slogan, invent the future, and turns that around in terms of big data and the past and the role of humans. So we should definitely keep that in mind here at Virginia Tech. Okay, so I'm going to start with the elector counting. And this gets a lot of attention in 1890. And it's also been recognized in any kind of history of computing or any kind of history data, any kind of history of statistics as this crucial turning point. And these illustrations on the left, which come from Scientific American, August 30th, 1890, you can see these a lot of places online. People have kind of abstracted this when they talk about this sequence of development of counting. The article on the right, those 2 columns that take up almost the whole page, are an explanation of how this electrical tabulation worked. And it can be redone as an algorithm, right? An algorithm as a step-by-step process for accomplishing some task. That's what they explain. And so the census starts with enumerators who go out all over the country. There are about 50,000 of them in June of 1890. And they have a set of questions. And they ask people to answer all those questions. They write down the information in them. Those get mailed to Washington in these big boxes. So we start down there on the bottom left. And then they are entered into a machine. So the person in the middle is just counting. She's just counting the number of names, the number of people in the household, and entering in this in the machine. And each time she pushes those buttons, the dials turn, and apparently a bell rings. That must drive people nuts, but that's what they said in the article. The next step, up to the top right, is when the data gets entered into a punch card. Right? And so they're reading this information off of he's reading the information off of the sheets. He's entering this information on this little machine, and the machine is actually punching holes in a card. And you can see an image of the card in the very top right. And that is now data about an individual, one person, okay? Age, place of birth, race, occupation, a whole series, birthplace of mother, birthplace of father, citizenship, a whole series of questions. And you could read this punch card with your eye if you knew where the information was and what it meant. And again, those of you who know history of computing, punch cards last through the 1970s, and maybe even the early 1980s, as a data storage method. They get replaced by tapes, they get replaced by disks, disk being the name of our data and social context program, and then the cloud, and so on and so forth. But in terms of a data storage moment, this is absolutely a key transition. And then you can read those cards, right? Because the machine looks through the holes in the punch card, it knows what it means, and then it starts to count. And so this is an algorithm for counting the census, moving through those different steps, which then produces a much greater volume of data that can be processed much more quickly, right? So if you think about big data and velocity and veracity and volume and so on and so forth, that's exactly what's going on here. And they make a big deal out of this, okay? So the end of the Scientific American article is saying, look how much faster we can measure and count and tabulate this data. That whereas once it would have taken days and weeks and months to do this, now we're doing it in a day or a couple days and so on. And one of the things that's interesting in these articles, which again is familiar to those of you who do history of computing, is that women were better at this than men. They counted up the number of names that could be done in a single day. The female clerks averaged about 47,000 names against 32,000 names. And this gets elaborated on later that summer when the Superintendent Porter, the director of the census, gives a speech in the summer. He talks about all of these issues about how much faster this is, but he makes the same point. Women average only 1/2 more than the men, that 38 of the 43 who counted more than 10,000 in a single day were women. He says women are better adapted for this particular work than men. They are more exact in touch, more expeditious handling the schedules, more at home and adjusting the delicate mechanisms of the machine, and apparently more ambitious to make a good record. So those of you who are interested in the trajectories of women in computer science, as you should be if you're sitting in this room, again, this is one of these crucial moments. Why were there so many women involved this time? What happened over a period of time? But really what they're interested in is the timing, okay? And part of the argument they made is that when you take humans out of this process, it's better, right? So if we think about humans and algorithms, this is a moment where they're making a very clear argument. If you take people out, it's faster, it's more accurate, it's more reliable, and so on. And you see a lot of newspaper articles that make this argument. There's a kind of gee whiz quality to these statements. We can do this so much better than we could. We can do it faster. This notion that electricity is now working for us, right? Machines are helping us think about what these numbers mean and why they matter. And again, all of these numbers about the volume is really the crucial thing. So this is where it starts. It starts with these questions, the 28 questions that every enumerator is asked to fill out for every individual or every household that he or she encounters in the course of collecting this data. And these, of course, this is one that gets added to the punch cards. This is the question that I became interested in. This is the race question. Whether white, black, mulatto, quadroon, octoroon, Chinese, Japanese, or Indian. Those were the meaningful racial categories in 1890 as determined by the law that tells the Census Bureau what information to collect. This is the only time these categories are used in the United States Census. And there's a couple places, the Pew Research Center and others have traced how these categories have changed and how we ended up with what we have now. But what interested me in terms of this workshop is, this is a formula, right? We're defining people by fractions. Are they colored? Are they black? Are they mulatto, which would be some combination of white and colored? Quadroon was one of 4 grandparents being colored, or octoroon, one of 8 grandparents being colored. Except it didn't really work that way, because according to the definition, to be in these other categories, one of your parents had to be white, right? And so as soon as they started to figure out what this meant, it suddenly got more complicated. But you can see evidence for that. As I said before, there are very few surviving individual records from the 1890 census. This is one of them that has the word octoroon in it, right? So if you read down the columns and left to right, this is where the race category is listed, and the mother in this case listed herself as mulatto, but then the 4 children were listed as octoroon, right? And so this is how we're classifying people in the context of this census. So you can find these census materials various ways. As I mentioned, you can go across the street to the library and find some of them. You can also find them from the Census Bureau website as PDF documents. Apparently in 2004, when they loaded these, you couldn't put more than 80 pages in a single PDF document. So 1,000-page books is like 12 different PDF documents, which is a pain in the neck, but there it is. What doesn't work in these is OCR, right? And so this bottom screen is the OCR version of one of these documents from HathiTrust, and they completely lose the tables. And so it's pretty useless. The scanning technology has gotten a little bit better, but I don't think we'll ever be able to scan these because the data as it's entered is really complex across these columns, and honestly, the quality of the text really makes OCR difficult, even if you had a way to arrange it by with a better scanner. And so what you end up doing, at least what I end up doing, is going through and re-entering all of this data by hand. And so this is what the table looks like with the classification by color, so total colored, persons of Negro descent, and then within that, total Negroes, mulattoes, quadroons, octoroons. And they have this for every state, this distribution. This is the numbers across the country in terms of the distribution at the time. The US population was about 12% colored across all of those categories. Within that, 85% were Negro, and then lower percentages for mulatto, for quadroons, for octoroons. The Chinese and Japanese populations were almost entirely in California at this time. In civilized Indians, we're not even going to talk about that. That's just really important and really complicated. This is the distribution among the states that had some of the highest colored populations, and again, primarily located in the US South for obvious reasons. This is 25 years after the Civil War. Mostly we're talking about the same states that had the slaves before the Civil War. This is a very familiar map showing this distribution of colored population by the total numbers. And again, showing the distribution pretty much across the Southeast United States. This is as a percent of the total population. So again, you see the same kind of distribution. So all of this is using census data from 1890 based on the categories and the columns that they included. At the time, they were really interested in data visualizations. And in fact, the large book here is almost entirely data visualizations from this census. And so this again shows you the distribution of the colored population in the United States. So the question I had is, how useful is this data for understanding not only what the population distribution is, but the accuracy of the numbers? Are these reliable numbers, right? And so I went back and re-entered all this data, looking at the top 20 states by colored population, and then did this both by the total number. So these are the two categories, the quadroons and the octoroons. As the total population, and then also as a percent of the total population. And what stood out is, why are there lower numbers here of quadroons in some states and higher numbers over here in these same states? To me, that doesn't make sense. If you look nationally, the one group is almost always higher, the other group is almost always lower. And if you pull this out, in most cases, the population of quadroons is higher, but there are a few where it's lower. California is one of them, and a few other places, and you can see the same thing here. I highlighted these. Why in North Carolina, for example, are the numbers much closer than they are in other states, South Carolina and Virginia? Why Ohio? Why Pennsylvania? Why Michigan, right? And so I'm using the data to ask some questions about, how was it collected? How were these categories defined? How did people understand it at the time? This is actually using it to think about what is a more common designation we use now in the census of 2 or more races, right? And so that's not the category they used, but by combining these, we can start to think about that. This is the same thing, again, east of the Mississippi. But again, it raises questions about the northern states. Why are they reporting these higher proportions in these different categories? This was something that interested the census, and this again comes from these documents in terms of how you define these questions. But what I really wanted to talk about, I'm going to finish with this, is this was an object of debate in 1890. This question of racial categorization and racial classification. How do you count people? And it first appeared in a Washington Post article that I've seen in June on 1890. The same article was then republished in a couple of newspapers across the United States and maybe more. And it starts with some of the same language in terms of the machine and the role of how much faster it was and so on and so forth. But then there is this lengthy discussion of this debate, because it's raised by a Mr. Lewis H. Douglas, who is the son of Frederick Douglass, who was a newspaperman in Washington, D.C., and a politician and activist. And he basically asked this question: why are you counting us this way? This is not who we are, right? You've got these categories, and they don't match up with our own experience. In color, they are neither white nor black. They are not mulattoes, quadroons, or octoroons, as those terms are defined in the dictionaries. What are they, and will the census of 1890 take notice of them? If so, under what head? And the answer from Superintendent Porter was, well, we didn't make up these categories. They were given to us, and if you don't answer this question, you don't count. Because if you don't answer this question using one of our categories, we don't have any way to measure who you are. So Douglas responds and says, this isn't about who we are. This isn't about color. And he goes through and he says the so-called color population in this country is a variety of shades from the whitest white to the blackest black as they draw near to or recede from the African or the Caucasian. The person who is not properly a mulatto, quadroon, or octoroon should be allowed to state, if of the African race more than the Caucasian, I am a black man with Caucasian blood in my veins, stating whatever fraction he can determine. So Douglas is really pushing back on data as a simplification of experience. He says, you've got these categories, they don't match up with who we are. We don't want to answer it in this way. And the response from Mr. Porter is, well, this is the only way we can count. We have to use these categories. And the reporter says, so it will be black or mixed? And Porter says, I don't see any way out of it. And they went back to Douglas's house, and his answer set was, I am neither. And Superintendent Porter says, well, that's the only answer of that character. He defines him as an outlier and says, you're not going to count. So we don't know what Douglas responded in the 1890 census because we don't have that records, but we can find his form from the 1900 census, and he actually answered the question as black. That's how he defined himself in the 1900 census. So this is what brought me back to the questions for this workshop. Okay, how do we think about the relationship between humans and algorithms? We need to think about them in context. We need to think not only about the role of the human being in creating and interpreting and analyzing these algorithms, but also the human being as the object of the algorithm. And how does the algorithm and the operation of that process simplify who people are, distort who they are, decontextualize who they are, take them out of the context, and the context is what makes it meaningful, and really produce an outcome that has long-lasting implications. So I'm going to stop there. Thank you.
We have time for some questions while the food gets here. So before Tom has to go catch his... No, you teach first. And then you go.
I don't know what I'm going to do next. Questions? Yeah.
Yes, thanks for the talk. Very interesting and impressive detective work to trace these responses through. So I'm curious about how you understand the importance of a couple of things. One of really elucidating the historical depth of these debates and the practices, datification, computation, and in terms of perceptions today, because there is often the sense that suddenly we have to think about the impact of basic methods on society. You're showing this has been going on for some time. And secondly, particularly in this context, you're looking at some of the debate and exchanges by specific historical actors, wondering how you assess the impact or significance this had more broadly for the U.S. population.
Wow. Okay. Let me try the first one, and I'll come back to the second one. I think sort of the question, the implications of datification, that's sort of what you're asking? Yeah, I think it matters a great deal. I think that as we think now about things like racial classifications or ethnicity, increasingly about gender classifications, we're appreciating the complexity of them and how difficult it is, to not only to define them in a way that are broad enough to be inclusive, but also to figure out where the boundaries are. And at the same time, you have people who say that doesn't apply to me. That's not who I am. And so where does that fit in? And I think there's a preference. And I'm going to say this as a non-computer scientist talking to a lot of computer scientists in the field to say, well, we're just not going to worry about those. They're outliers. They don't fit. They're not clean. We need clean data to run what we're doing, and so we're not going to worry about them. As a historian, as a humanist, that's what interests me. Like where do those people fit in these categories? And Lewis Douglas is in effect saying that. So I think that's one thing we want to keep coming back to. And anytime you're looking at historical data, and all data is historical, Kathy O'Neill makes that point really well, you have to ask who was included, but also who was excluded in that process, and how do you factor that in, whether you're doing some kind of demographic or statistical analysis, or whether that's the data you're using to train a classifier. Right? And so I think we have to keep asking these questions about the datification as a process. And this is going to matter tremendously in the 2020 census, right? Because we put in a citizenship question, that's really going to affect how people answer. The question about immigration status is going to affect. All of these things are going to matter. And what really interests me in terms of reading Lewis Douglas's statement and then thinking about the contemporary debates is that was data refusal, what he was doing, right? He's saying, you're asking me a question, and I'm saying I'm none of these things. And so when we think about data refusal now, and when you log into something, or when you sign up for something and it asks for date of birth and gender, and do you answer those questions? Because what's going to happen to that data as you go forward? And so I think the 1890 census and subsequent is a really important moment in datification, but it's also a moment in some ways of data refusal. That's going to continue on. So I think those are broadly those kinds of questions. Remind me of the second question.
So why does it matter
Why does it matter?
there's historical data?
Yeah. Yeah, I think it matters. It matters from my perspective to both of the fields I'm trying to talk to. I think for the humanities and for the historians, we need to be much more appreciative of how algorithms work. Not only in the past, but moving forward and into the future, because so much more of what we're doing is shaped by them. And so I think if we go back and say, where do they matter and how have they affected us, that's going to help us train students, be better citizens, and so on and so forth. I think, again, from the computational side, appreciating, the complexity and the context. Adam started with, data is complex and messy. That's my starting point. Right? Data is complex and messy because the contexts matter for that. And so I think the more, from the humanities side, we can inform the computational scholars of how this works and why it's messy, the better than the algorithms can be done. Thank you. Other questions? Yes?
Thinking on what you were just saying, do you think that explicit data refusal ought to be built into our data collection method, our data collection methods as a general practice? And what I'm thinking is our automated data, the kind of data collection that websites routinely engage in, that we have to engage in to be members of the Virginia Tech community because of decisions that were made about what software we can use and so forth and so on.
Yes. What that means and how.
Say that explicitly.
I appreciate that. What that means, how it is put into operation, the implications of that. Those are obviously the complicating factors. And there is no, in the 1890 census as now, there is no legal obligation to answer, right? The only consequence of not answering is people then come to your door and ask you questions and so on and so forth. And so that puts it in a completely different category from, what we ask students to do every time they log in. If we ask them to use Canvas, if we ask them to use Google Docs, if we ask them to use something like TipTop or whatever, the share, anytime we ask them to do that, we are requiring them to make their data available in some form. And I think we need to be very conscious of that. If you go beyond students and talk about, data collection for a research project or something else, you're going to have more, have more guidelines and rules in terms of institutional review board and human subject and so on and so forth. But anytime you're, asking people to provide that information, you have to be very aware of what information are they being asked to do and how to handle it. And then, what do you do about data refusal? I don't think we have I at least don't have a good explanation or a good response to that, certainly in the context of a teaching situation or something else. Part of the reason I look at the 1890 census is there is not the question of human subjects. They're all they're all dead. But it would be very different if you were doing this with the 2010 census or the 2000 census or those kinds of issues.
We have time for one more question, and the update is that food is coming, so it's not too late.
Keep talking. Yes.
Again, a very interesting talk. I'm just wondering, based on the data that you showed, I found it interesting because you can actually use that to project geopolitical climate of the day. For example, the Asians make up such a small percentage back in 1890, and yet they separated Chinese and Japanese because it's right before the Opium War.
Mm-hmm.
And I'm just wondering, in the U.S., was there a time where they actually distinguished Caucasians into, Scandinavian, Italian, or whatever? Was there ever a time such as that, because of wars or whatever?
Yes. Several different versions, right? So the big distinction among the white population is right here, which is native parents and foreign parents. And this is a high level of immigration to the United States, 1870s, 1880s, 1890s. It's just shifting from primarily Anglo-Saxon, North, UK and Germany, France, into Southeastern Europe. So they're very concerned. And a lot of the data in there is actually tracing not just immigrants and native, but immigrants by place of birth of mother. And so they really want to look at the Scandinavians and so on and so forth. It's not so much political as it is eugenics. And this argument that people of certain ethnicities are by nature more healthier, more intelligent, kind of a whole series of things. So that's where that factors in. I don't know enough on the Asian classifications to say when that distinction started or then how it evolves over the course of the census. Certainly in the case of civilized Indians, that's what's going on there also. So it is very political, absolutely. But it's very, and this goes back to what I was saying earlier, the way that the categories are defined is a response to contextual factors. And so if there's anxiety about immigration, that's what they're going to be looking for. If there's anxiety about the African American population after emancipation, after slavery, that's what they're going to be looking for. And this census is also significant because of all the attention to crime and the relationship between crime and ethnicity and race. So yeah, it's very much shaped by those factors. And I didn't talk about it, but I put this last statement up here. There's a kind of imperialist sense here, because now we've gotten so good at counting ourselves, we can use these tools to count the rest of the world. And it wouldn't even take us that very, very long because we have these machines. But if you look at the language down there, the 650 million people could thus be counted by the same staff in 100 days, and the entire population of the Earth, which including Asiatics and savages, is estimated at 1.3 billion. So that's just common language in this context. But what's interesting to me, and this goes back in some ways to Dr. Johnson's question, you have this racist language that is not only normal and perfectly accepted, but now it's being brought into statistics, which then appears scientific.
All right, they're setting up lunch, so you decide if you want to take a break or you want to ask Tom another question.
Do you have a question?
Yeah, I have a question. I was wondering how you think about the relationship between the concept of data refusal and the concept of representation.
Mm-hmm. Sure.
And, so for instance, in Census Materials, we see under-participation in rural places.
Mm-hmm.
And Wikipedia is a huge data set that's used to train NLP algorithms and all kinds of other things, right? And so, on the one hand, yes, either through non-participation or through an active choice of refusal, people are choosing to refuse to participate to some extent, right? What that leads to underrepresentation or misrepresentation outcomes as a data platform, data set, right? And so I'm wondering how you think about the tension between those two things, and sort of what us as computer scientists maybe should be thinking about, or how to approach this.
Yeah. So that's a good question with lots of layers to it. And I think, a common term, and we heard it some this morning, has to do with bias, within the data set or within the way it's being used. And that's not a term I use very much because history, everything in history is biased. And so to talk about bias is sort of self-evident. You know, I'll talk more in terms of perspectives, representation works there, participation. And so, you know, to take your example, which I don't know much about, but in terms of who the authors are and the editors are and so on and so forth in Wikipedia, absolutely. You know, if you're using that as a data set, you have to know who's generating that information, who's using that information, how that information is being interpreted, and so on and so forth. You know, I think with the census, there are ways to compare numbers, and to some extent that's what I was doing in the earlier project, because if we got a set of data about deaths from this source, we got a set of data from deaths about this source, it's not so much which one is right, but where are they getting information and how can we compare them. And so again, to take this example, you know, what would be an alternative set of data that the groups that are not represented in this area are represented in this area, and how could you bring that into your discussion and bring that into your data set, but in a way that you know, puts them on an equal footing in terms of their levels of representation. And certainly, you know, if you're using that language to train the algorithm, train the classifier, you have to be aware of that, or you're going to reproduce these discrepancies as you move through. All right. Thank you very much.
Thank you, Tom. So lunch is here, and then we'll be getting back here again.